we're going to take a look at pH and pOH calculations. So our goal is to be able to calculate the concentration of hydronium hydroxide ions and pH and pOH for acidic and basic solutions. Water is polar and therefore ionizes to a very small degree. What this means is when we have just pure water, if we were to test the conductivity, we would expect, because it's molecular, that there would be no ions and therefore no conductivity. However, what we see is that water does slightly conduct electricity. So over time, what they decided, or figured out, I guess, is that two water molecules together will make H3O plus and OH minus. What was happening here is that water comes near another water, and because this is partially negative and this hydrogen is partially positive, they are attracted to one another. And every once in a while, which is what this symbol means, it means that it does not go to completion like a regular arrow, that it can go both forwards and backwards. So in some cases, what's going to happen is that the one water molecule joins up with an H from the other water molecule, and we make H3O plus, and we're left with, at this case, an OH minus. So what's happened is water has stolen one H and left an OH minus behind. Now, because there's a small amount of these in water, it's able to conduct because these are charged particles. So a hydronium ion is this H3O plus. So hydronium. And we made, again, hydroxide. Now, notice how closely these are related in terms of how they spelled and how they sound. So be careful when you're listening or reading something that you are paying attention to whether it's asking for hydronium or hydroxide. So it says in pure water at SATP, so that's like general conditions, lab conditions, nothing fancy in terms of temperature or pressure. The hydronium ion concentration is very low because only 2 water molecules in 1 billion will ionize to make these. So only 2 in 1 billion will actually undergo this reaction. The rest of water just stays as regular water. Because it makes an equal number of H3Os and OH minus, we can say that the concentration of H3Os and the concentration of OH minus in solution are equal. And with experimentation, they've decided that the concentration of each of these is 1 × 10 to the negative 7 moles per liter. So a neutral solution, we're looking for the H3O plus concentration here and the pH. I know that the pH is 7. For an acidic solution, it will be less than 7. And for a basic solution, it will be greater than 7. Now, what is the H3O concentration of a neutral solution? Well, we just saw that the concentration of H3O plus is equal to the concentration of OH minus in water, which is 1 × 10 to the negative 7 moles per liter. We know that water is neutral. So the H3O plus concentration for a neutral solution should be about 1 × 10 to the negative 7 moles per liter. Now, if it's acidic, it has more H3O plus than a neutral solution. Therefore, the concentration of H3O will be greater than 1 × 10 to the negative 7 moles per liter. And a basic solution will have a concentration of H3O plus that's very low. It doesn't have as many acid molecules. So it will be less than 1 × 10 to the negative 7 moles per liter. Now note that if something is less than 1 × 10 to the negative 7, it ends up getting a greater exponent because that's just more zeros in front of it, right? Right, so something like this, moles per liter, this is a real concentration, has a concentration of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1 × 10 to the negative 12 moles per liter would fit this bill. Now, this exponent is greater than 7 when it's basic, and the pH is greater than 7 when it's basic. Keep that idea in mind. If something's acidic, its concentration is greater than 1 times 10 to the negative 7. So maybe it's 0.0001, which is 1 times 10 to the negative 4 moles per liter. Now that is a smaller number than 7, and our pH is less than 7. So maybe the exponent in the concentration and the pH value are related. Well, we know the greater the concentration of H3O plus or hydronium, the more acidic a solution is. In acidic solutions, the concentration of H3O is greater than the OH minus concentration. The lower the H3O plus or hydronium ion concentration, or the greater the OH minus concentration, the more basic a solution is. In basic solutions, the concentration of H3O plus is less than the concentration of OH minus. When they are equal to one another, the concentration of H3O and OH minus, like we saw in water, the solution is neutral. So pH is a shorthand method of communicating the hydronium ion concentration of a solution. A logarithmic scale is used to simplify the range of H3O plus and OH minus to a scale between 0 and 14. We've seen logarithmic scales recently in the measurement of cases of coronavirus. It allows them to draw a scale that's a lot more reasonable rather than drawing increments of 1,000. If it goes up by powers of 10, we could go from 10 to 100 to 1,000. Then the next increment is 10,000. So the scale is a little bit different than our typical scale. This is related to pH, but I won't go into more specifics. The measurement of pH has no units, yay. And in general, the concentration exponent equals the pH. So when we had something like this for the concentration of H3O plus, we can say that the pH is 7. So note that this is only useful when the pH values are simple factors of 1 and the concentrations are powers of 10. So this has to be a 1 times 10 to the 7. I can't say that the pH is 7 when it's 2 times 10 to the 7, or when it's 0.00001 times 10 to the negative 7. I cannot say that the pH is 7. It has to be exactly 1. So using that idea, we can decide the pH values of these concentrations. So if the H3O plus concentration is 1 times 10 to the negative 8, the pH is the exponent, so 8. That means that this solution is basic. If the concentration is 1 times 10 to the negative 4, the pH is 4. Therefore, this is an acidic solution. If it is 1 times 10 to the negative 7, that is a neutral solution. Again, it only works for powers of 1. A change in pH of 1 is equivalent to a 10-fold change in the hydronium ion concentration. So how much would the hydronium ion concentration change if the pH decreases from 6 to 3? I'm going to give myself some more room here. So if the pH decreases from 6 to 3, I could say that the hydronium ion concentration at the pH of 6 is 1 times 10 to the negative 6 moles per liter. At a pH of 5, it was 1 times 10 to the negative 5 moles per liter, 1 times 10 to the negative 4 moles per liter, and 1 times 10 to the negative 3 moles per liter. To get from negative 6 to negative 5, we must multiply by 10. To get from negative 5 to negative 4, we must multiply by another 10, and lastly, by another 10. So to get from our concentration of a pH of 6 to a concentration where the pH was 3, we multiplied by 10 3 times, which is like multiplying by 10 to the 3. So this is an increase because the pH, the concentration is getting larger. Okay, so the concentration of H3O plus is increasing by a factor of 10 to the 3. Now, if the pH increases from 8 to 12, what is happening to the hydronium ion concentration? Well, 8, 9, 10, 11, 12. Again, my concentration here is 1 times 10 to the negative 8, 1 times 10 to the negative 9, 1 times 10 to the negative 10, 1 times 10 to the negative 11, and 1 times 10 to the negative 12. So in this case, we have, I'm just going to write underneath, we've divided by 10 to get a smaller concentration each time. So divide by 10, divide by 10, divide by 10. Dividing by 10 4 times is equivalent to dividing by 10 to the 4. So our concentration of H3O plus has decreased by a factor of 10 to the 4 because we've had to divide. Now, an easy way to remember this is if we do every time we change, it's a factor of 10. 10, in this case, 6 minus 3. So we're changing the pH by 6 to 3. So we go 10 to the power of 3, and that is an increase. It's a positive exponent. Over here, we go from from 8 to 12, and we subtract those two, and we get 10 to the negative 4, which is exactly equal to 1 over 10 to the 4, using our math brain. So just by subtracting the two pH values and putting them to an exponent of 10, we can decide if it's increased or decreased, and by how much. Significant digits. The number of digits following the decimal point in the pH is equal to the number of significant digits in the hydronium ion concentration. What? So an example will help us here. Let's say we have a pH of 1.4372. This gives us an H3O plus concentration of 0.03654 moles per liter. Now, this is correct significant digits. So in our H3O plus concentration, the zeros don't count. They are leading zeros. So I have 4 significant figures here. Again, the zeros do not count. In my pH, what this is saying is that the decimal places following are significant. So there are 4 significant figures here. We do not count anything before the decimal. Another example, if I have let's say an H3O plus concentration of 1.00 times 10 to the negative 13 moles per liter, I know that the pH will be 13 because this is an exact factor of 1, and we just use its exponent. But I don't want to just write 13. That's not correct significant digits. In my concentration of H3O, there are 3 significant digits. That means that in my pH, I must have 3 decimal places, and those will just be zeros in this case. Because our decimal places are significant figures, the first 2 values are not. So anything before our decimal places does not count as a significant figure. So to find the pH of something, we're going to use the negative log of the concentration of H3O plus. The log button is beside the 7 on your TI calculator. Log and ln below are different, so make sure that you're using the log button. So given a hydronium ion concentration of 6.7 times 10 to the negative 8 moles per liter, calculate the pH. Again, pH is the negative log of the concentration of H3O plus. So this is the negative log of 6.7 times 10 to the negative 8 moles per liter. How many significant digits do we have in our concentration? We have 2. Therefore, we must report our pH value to 2 decimal places. The pH is 7.17, Again, this 7 is not a significant digit. It is only the decimal places here. Determine the pH of a 4.7 times 10 to the negative 4 moles per liter solution of nitric acid. Well, we need the concentration of H3O plus for nitric acid. So what we're going to do is we're going to write the dissociation equation for nitric acid. We get that H plus and NO3 minus. There's no H3O plus. However, what we know is that the concentration of H plus can be said to be equal to H3O plus concentration. So the hydrogen ion and the hydronium ion have an equal concentration, and we'll talk about this in lesson 3 when we talk about the Arrhenius theory. So we were given the concentration of HNO3. So the concentration here was 4.7 times 10 to the negative 4 moles per liter. To calculate a pH, we need the negative log of the H3O plus concentration, which we know we can just use H plus. So we need the concentration of H plus. In this case, it looks very straightforward. We have 4.7 times 10 to the negative 4 moles per liter of HNO3 and a 1-to-1 ratio to convert to H3O plus. So there's 1 mole of HNO3 reacting to make 1 mole of H plus. Therefore, the concentration of H plus is just going to be the same. So 4.7 times 10 to the negative 4 moles per liter. And that's what we can put in to our pH formula. Times 10 to the negative 4 moles per liter. And we need to decide how many significant digits we get. There were 2 significant figures in our concentration here. Therefore, we get to keep 2 decimal places for our pH value. So our pH is 3.33. Don't forget to convert if you're given the concentration of a compound, not the acidic or, in the end, basic ion. How do we go backwards? What happens if you were just given a pH and asked to find the concentration of H3O plus, or remember, the concentration of H plus? Well, we can use 10 to the negative pH. So to get this, you can just say second log, and that will bring up the 10 to the power button. So a solution has a pH of 10.3. Calculate its hydronium ion concentration. Well, concentration of H3O plus is equal to 10 to the power of the negative pH. So 10 to the negative 10.3 will be our concentration, which with significant digits, there is only 1 in our pH value. Therefore, we get to keep 1 significant digit in our concentration. So 5 times 10 to the negative 11, my mistake, moles per liter. What is the concentration of a hydrochloric acid solution with a pH of 3.10? Well, we can find the concentration of H3O plus from our pH. So 10 to the negative pH. So 10 to the negative 3.10 gives us a concentration of 7.9 times 10 to the negative 4 moles per liter. Again, there are 2 significant digits in our pH because there's 2 decimal places. So 2 significant digits in our concentration. Now this is the concentration of H3O plus, the hydronium ion. It is not the concentration of HCl. So we need to show that HCl dissociates into H plus and Cl minus. I have the concentration of H3O, which is equal to the concentration of H plus. So we need to find the concentration of HCl. This is just our concentration of ions. So 7.9 times 10 to the negative 4, oops, forgot my negative there, moles of H plus per 1 liter. There's 1 mole of H plus per 1 mole of HCl. Therefore, our concentrations are equal. 7.9 times 10 to the negative 4 moles per liter is the concentration of HCl. What about bases? So we can use the formulas very similarly for pH to find the pOH, which is just a relationship for bases. whereas pH was a relationship for acids. We just use pH to describe everything. All right, so pOH is the negative log of the OH minus concentration. Just the same, but different ions. The concentration of OH minus is the negative 10 to the negative pOH. Now, how do we know that we use pH for everything, all basic solutions included? How are these related? Well, the pH and the pOH add to 14. Note that you can have a negative pH and a negative pOH, or you could have something off of the scale of 14. It is possible. So don't be alarmed if you ever get that as an answer. However, these two will always add to 14. The hydroxide ion concentration of a cleaning solution is determined to be 0.27 moles per liter. What is its pOH? So hydroxide ion is OH minus. pOH is the negative log of the hydroxide ion concentration. So this is the negative log of 0.27 moles per liter. The pOH in this case, we have 2 significant digits in our concentration, so we need 2 decimal places in our pOH. Same idea for significant digits. So 0.57 should be our calculated pOH. A sample of water has a pOH of 6.341. Calculate the hydroxide ion concentration. So OH minus is 10 to the negative pOH, which we have. So 10 to the negative 6.341. There are 3 decimals for our pOH. Therefore, we need 3 significant digits for our concentration. So 4.56 times 10 to the negative 7 moles per liter. pH. If a sample of wastewater has a pOH of 4.0285, what is the concentration of hydronium ion in the solution? So pOH, if I have the pOH, I can calculate the OH minus concentration only. Now that is not the same as the hydronium ion concentration, so I don't want to do this. What we know from our formulas is that if I have OH minus, I can calculate the pOH. So I can go both directions here. I can either take the pOH and calculate the concentration of OH minus, or I can take the OH minus concentration and calculate pOH. I can also use the pH to calculate the concentration of H3O plus using the concentration of pH formula. Okay, or 10 to the... All right, and we can relate the two of these using our pH plus pOH is 14. And that's what we need to do. So we have a pOH here. We are looking for the H3O plus concentration. So our first step is to use pH and pOH adding to 14 to find a pH value. So pH will be equal to 14 minus the pOH, which is 14 take away 4.0285, and we get 9.9715 for a pH. From pH, I can calculate the H3O plus concentration using 10 to the negative pH. So 10 to the negative 9.9715, and we get 1.068 times 10 to the negative 10 moles per liter. Again, there were 4 decimal places in my pOH. Therefore, there can be 4 significant digits in my concentration. All right, there's a few more extension problems here to get us a little bit further with these formulas. So calculate the mass of NaOH dissolved in 250 milliliters of water to have a pH of 13.501. Well, is NaOH an acid or a base? What we can start with is its dissociation equation. So NaOH as a solid can be dissolved in water, it is soluble, to make Na plus and OH minus. The presence of OH minus tells me it's a base, and the fact that the pH is here tells me it is a base. If I'm working with a base, I want to turn pH into a pOH because, remember, If I have a pH, I can convert to a pOH, and with a pOH, I can find the concentration of OH minus. If I find the concentration of OH minus, I can then relate it back to the amount of NaOH dissolved in water. So let's start there. Let's convert this from a pH to a pOH. So pOH is equal to 14 minus our pH, which is 14 minus 13.501. And I get a pOH of 0.499. With my pOH, I can find the concentration of OH minus using 10 to the negative pOH. So 10 to the negative 0.499 is equal to 0.31696 moles per liter. And that's of NaOH. OH minus, my mistake. This isn't my final answer, so I didn't worry about my significant digits. Once I have the concentration of OH minus, I can use my mole ratio to convert back to the concentration of NaOH. So 0.31696 moles per liter of OH minus times 1 mole of OH minus per 1 mole of NaOH. And we get 0.31696 moles per liter of NaOH. Once I have the concentration of NaOH, I also have the volume. I can find moles, and I can use my molar mass to find the mass. So C equals N over V. N is equal to C times V. 31696 moles per liter times 0.250 liters. And we get 0.07924 moles. And last but not least, using N is equal to little m over big M, and it's all for mass. So 0.07924 moles times the molar mass is 40. And I get 3.1696 grams. Our final answer should have 3 significant digits because there are 3 decimal places in my pH value. So our final answer is 3.17 grams of NaOH dissolved in 250 milliliters of water. This one was tricky. We had a lot going on here. So let's calculate the pOH of a solution where 10.3 grams of calcium hydroxide is dissolved in 500 milliliters of water. If we're looking for pOH, we need the concentration of OH minus, or we need a pH value. So we need to decide, is this an acid or a base? So let's write out its dissociation equation. It dissociates into calcium 2 plus and 2 OH minus. The fact that it has an OH minus tells me it's a base. So if I can find the concentration of OH minus, I can find the pOH. So this is our goal, is find the concentration of this. We were given a mass of 10.3 grams of calcium hydroxide, and this is all dissolved in 500 milliliters of water. So I don't know, I'll put that here. So let's find the concentration of OH minus. So I'm going to use unit analysis here. I have its molar mass. I've calculated that as well. It's 74.10 grams per mole. So let's start with its mass. 10.3 grams times 74.10 grams per 1 mole, and that's of calcium hydroxide. So let's find its concentration. Cancel grams. Now we can either switch to moles of hydroxide and then find volume, or we can find concentration of calcium hydroxide and then switch. So maybe I will do kind of our typical stoich here. So I'm going to switch to moles of hydroxide. So there is 1 mole of calcium hydroxide per 2 moles of OH minus. Now, solution stoic, if I want to end up with a concentration, I need units of moles per liter. So moles need to stay as a unit, and I need to divide by liters. So if I change my concentration into liters and put a placeholder 1, that will do. All right, the biggest thing here is that our mole ratio is not 1-to-1, which is pretty much everything we've seen thus far in this topic. So you have to be careful that we're actually making twice as many OHs. However you've calculated this out, whether you used formulas or unit analysis, make sure that you have that mole ratio in there. We get a concentration of OH minus of 0.5560 moles per liter. So I'm going to write that in, 0.5560 moles per liter. Now that I have the concentration of OH minus, I can find the pOH. Negative log of that value. The square brackets just mean concentration, so you can use whatever brackets you want when you sub in a number. And that will equal a pOH of 0.255. 3 decimal places because there are 3 significant digits. Last one. Calculate the mass of gaseous hydrogen chloride dissolved in 10 liters of water to have a measured pH of 2.603. If I have a pH, I can find the concentration of H3O+, which remember is the same as the concentration of H+. But it can also be related to pOH, which can be related to the concentration of OH minus. We need to decide, is hydrogen chloride an acid or a base? Hydrogen chloride is HCl. When it is dissolved in water, it makes H+ and Cl-. So I see H+, therefore it's an acid. So I'm going to use this pH value and I'm going to turn that into the concentration of H3O+. So concentration of H3O+ is equal to 10 to the negative pH, which is 10 to the negative 2.603. So I get a concentration of 0.002495 moles per liter. All right, that's the concentration of H3O or H+. So if I want to convert to the concentration of HCl, we can. So the concentration, 0.02495 moles of H+ per 1 liter times 1 mole of H+ per 1 mole of HCl. 1-to-1 here, nice and easy. All right, so now that I have a concentration of HCl, we know that this is in a volume of 10 liters. We have its concentration, and I know its molar mass is 36.46 grams per mole. So 10 liters times its concentration, 0.002495 moles of HCl per 1 liter. Liters cancel. Times by its molar mass of 36.46 grams per 1 mole. And I get 0.910 grams of HCl in 10 liters to give a pH of 2.603, which isn't very much, it seems. Make sure you try some of the practice problems. I did the putting it all together here. If you want to take another stab at it on your own or just review it again, and then make sure you try the practice in the textbook.